All right, so this example is in your book. I mean, a lot of these examples that I use are in your book, but this one is one of those special ones where I showed you it's a elastic collision. So you have both conservation of momentum and conservation of kinetic energy. And then from those two equations, they then do a fancy algebra, and then they end up with these kind of crazy equations at the end that you can memorize, and it makes these problems much, much simpler. So the way that they do it in your book, which is on page 239, is the easy way to do it. I'm going to show you how to do it the more complicated way, so that if you don't remember those equations, you can still do these problems. It's just that algebra's ugly. So it's possible. It's just not as easy. So let's do it. Okay, so we have in this figure, block 1 approaches a line of two stationary blocks with a velocity v1 initial of 10 meters per second. So we're going to have two collisions here, okay? It collides with block 2, which then collides with block 3, which has a mass m3 of 6 kilograms. After the second collision, block 2 is again stationary, and block 3 has a velocity v3 final of 5 meters per second. Assume that the collisions are elastic. So since they tell you that, that should kind of, ring bells in your head saying that not only momentum is conserved, but also kinetic energy is conserved as well. And we want to know, what are the masses of blocks 1 and 2, and what is the final velocity v1 final of block 1? So again, we have two collisions here. So for collision number 1, and then we have collision number 2. So for collision number 1, it says V1 initial is 10 meters per second. And then we know that both block 2 and block 3 are initially stationary. So because of that, my V2 initial is 0. Now it then tells me that block 1 collides with block 2, which then collides with block 3. And then after the second collision, block 2 is stationary. So we don't know what the final velocity of block 2 is, or block 1 is, after collision number 1. So that's all the information we know about collision number 1, which is not much because we don't know the masses either. Now for collision number 2, it tells us that block 2 collides with block 3, which has a mass, so M3 is 6 kilograms. And then it says that after the second collision, block 2 is again stationary. So that means that V final 2 is equal to 0 for collision number 2, not for collision number 1. And then it says, and block 3 has a velocity V3 final of 5 meters per second. So final velocity of 3 is 5 meters per second. And then we also know that it was initially stationary, so therefore V initial 3 is 0. Do we know anything else? Assume that the collisions are elastic. So no, that's all we know about collision number 2. So we also don't know much about collision number 2, but we know much more about collision number 2 than we do about collision number 1. So because these are both elastic, like I said, we have conservation of momentum and we have conservation of kinetic energy. So what we're going to do is we're going to start with the collision that we know more about, and then we're going to kind of work backwards almost. Now, the other thing that we know is that since we have two collisions that happen in succession, that means that the final velocity of block 2 will then be the initial velocity for collision number 2. Right? Because that block 2 then goes on to collide with block 3. So once we get the initial velocity for block number 2, for collision number 2, we can then use that in collision number 1. So we're going to start here. So I have, for collision number 2, I have mass 2, V initial 2, plus mass 3, V initial 3, equals mass 2, V final 2, plus mass 3, V final 3. So this is conservation of momentum. So I know that the final velocity of block 2 is 0, so this whole term cancels out. I also know that the initial velocity for block 3 is 0. So this whole term cancels out, which helps us because it simplifies our equation way down, right? So we get mass 2 V initial 2 equals mass 3 V final 3. Now that's conservation of momentum. We also have conservation of kinetic energy. That means that kinetic energy initial equals kinetic energy final. So we get 1/2 m2 V initial 2 squared plus 1/2 m3 V initial 3 squared equals 1/2 m2 V final 2 squared plus 1/2 m3 V final 3 squared. Now here, 1/2s all cancel out, which makes that easy. And again, we also know that the initial velocity of 3 is 0, so this whole term cancels out to 0, and the final velocity of 2 is 0, so that whole term cancels out to 0. So this ends up simplifying to mass 2 V initial 2 squared plus, equals mass 3 V final 3 squared. So I have two equations and I have two unknowns because I know what mass 3 is and I know what V final 3 is. So what we're going to do now is I'm going to plug in for the first equation, our conservation of momentum. I'm going to plug in mass 3 and V final 3. So what I get here is mass 2, V initial 2 equals mass 3, which was 6 kilograms, times V final 3, which was 5 meters per second. And so here I get mass 2 V initial 2 equals 30 kilograms times meters per second. So here what I'm going to do is I'm actually going to solve this equation now for either mass 2 or V initial 2. I'm going to solve this for mass 2 just because in the other equation, V initial 2 is squared, which just kind of makes things complicated. You can do either one though, they both work out, doesn't really matter. So I get mass 2 is equal to 30 divided by V initial 2. So I'm going to take this now and I'm going to plug that in here and also plug in my other nodes. So what I get here is 30 divided by V initial 2 times V initial 2 squared equals mass 3, which was again 6 kilograms, times V final 3, which was 5 meters per second squared. Here, this V initial 2 on the denominator cancels out with that squared there, and I end up getting 30 times V initial 2 equals 6 times 5 times 5, which is 150 kilograms times meters squared per second squared. We'll just leave off the units for now. And then we're going to divide both sides by 30. And we get 150 divided by 30, which is V initial 2 is 5 meters per second. So V initial 2, 5 meters per second, which is the same as V final 3, which is interesting. And then what we're going to do is we're going to take this, and then now we're going to plug this in back for here. And so we get M2 equals 30 divided by 5 meters per second, which ends up being 6 kilograms for M2. All right. So we've already got a lot more information than we had before. And we've answered some of our questions too, right? Because I want to know what are the masses of blocks 1 and block 2. And then we also want to know what the final velocity V1 final is of block 1. So we know the mass of block 2 now. It is 6 kilograms, same mass as block number 3. So now we're going to apply these things to collision number 1. So I already know from collision number 1, and I'm going to write it back down below here. I already know from collision number 1 that the initial velocity of block 1 is 10 meters per second. I also know that the initial velocity of block 2 is 0. And then I just learned that the final velocity of block 2 is 5 meters per second. Because remember, the initial velocity for block 2 for collision number 2 is the final velocity for block 2 for collision number 1. So that's our final velocity of block 2. And then I also know the mass of block 2, and that was 6 kilograms. Whoa, what was that? So the things that I don't know still are m1 is question mark, and then we also don't know the final velocity for 1. Right? But again, this is also a elastic collision. So because of that, again, both momentum and our kinetic energy are conserved. So we're going to do the same thing that we did in the first example, except it gets even more complicated this time because now we only have one thing that's 0 here. So not as much stuff is going to cancel out as before. So let's start with our conservation of momentum. So I know momentum initial equals momentum final. Here I get mass 1 v initial 1 plus mass 2 v initial 2 equals mass 1 v final 1 plus mass 2 v final 2. And then the only thing that is 0 here is v initial 2, so we can cancel that term out. So this whole thing is 0. And so this reduces down to mass 1 v initial 1 equals mass 1 v final 1 plus mass 2 v final 2. Now, of course, we know a couple things here now. We know the final velocity of mass 2. We know the mass of mass 2. We also know the initial velocity of mass 1, so I can plug those things in. So I get mass 1 times 10 meters per second equals mass 1 times v final 1 plus mass 2, which was 6 kilograms, times final velocity of 2, which was 5 meters per second. So here we get 10 m1 equals m1 v final 1 plus 30. All right, so there's our conservation of momentum. Now we can't do much else with this because we don't know what mass 1 is and we don't know what final velocity of 1 is. So now I'm going to move on to my conservation of kinetic energy. So again, I know kinetic energy initial equals kinetic energy final for a elastic collision. So here I get 1/2 m1 v1 initial squared plus 1/2 m2 v initial 2 squared equals 1/2 m1 v final 1 squared plus 1/2 m2 v final 2 squared. Again, 1/2s all cancel out, and also our initial velocity of 2 cancels out. And then so here, I'm also going to plug in our knowns. So we know m1, we know the initial velocity of 1 is 10. So I get 10 squared equals m1 v final 1 squared plus m2, which was 6, times final velocity of 2, which was 5, and then we're going to square that. So we get 100 m1 equals m1 v final 1 squared plus, what is that, 150. Okay, now again, I have 2 equations and 2 unknowns. So what I need to do now is just what I did before. I'm going to solve the first equation for one of those variables, plug it into the second equation. Now again, like I said, it doesn't look as pretty as it did before, but it's okay, it still works out. So I'm going to take this equation here. I'm going to subtract m1 v final 1 from both sides in order to solve for m1. So I get 10 m1 minus m1 v final 1 equals 30. I'm then going to factor out, oh my gosh, I'm running out of room. I'm factoring out an m1. So I get 10 minus v final 1 equals 30. And so here I get m1 equals 30 divided by 10 minus v final 1. So now this term right here is then going to go into both the m1s here and here. I'll do this in a different color. So we get 100 times 30 divided by 10 minus v final 1 equals mass 1, which again was 30 divided by 10 minus v final 1 times v final 1 squared plus 150. Now for algebra. So 100 times 30, that is 3,000. So we get 3,000 divided by 10 minus v final 1 equals 30 times v final 1 squared over 10 minus v final 1 plus 150. We can then multiply every term here by 10 minus v final 1 in order to get rid of it on the denominator there. So if we do that, so I'm multiplying everything through by 10 minus v final 1. And so they cancel out on the denominators of those two fractions, and then we're just going to multiply 150 by 10 minus v final 1. So what we get here is 3,000 equals 30 v final 1 squared plus 150 times the quantity 10 minus v final 1. So we're getting there, we're getting somewhere. So the next thing we're going to do is we are going to multiply, we're going to distribute that 150. So we end up getting 1,500 minus 150 times v final 1. And so we get 3,000 equals 30 v final 1 squared plus 1,500 minus 150 v final 1. And then now this is pretty ugly. What we're going to do now is divide every single term here by 30. Okay, so we're going to divide all the terms by 30 because 30 goes into every single one of those. And I'm going to open up a new page if I can. How do I do this? Can I? Let's go here. So we are now going to divide everything by 30. So what we end up getting here is 100 equals v final 1 squared plus 50 minus 5 v final 1. So I just divided every single term by 30. Now here, this is starting to look a little bit more manageable, right? Because we're seeing that, okay, we're going to get a quadratic here. So what we get is v final 1 squared minus 5 v final 1. And then I'm subtracting 100 from both sides, so minus 50 equals 0. And then doing the quadratic formula the old school way, x equals negative b plus or minus square root b squared minus 4 times a times c all over 2a. So we get 25, 5 times 5, right, b squared, minus 4 times 1 times negative 50. So really I'm adding, so 25 plus 4 times 50. I get 225 under the square root. Taking the square root of that, I get 15. So we get x equals 5 plus or minus 15. Divided by 2. And here we're talking about a velocity, right? That's what x is. So velocities can be either positive or negative. So because of that, we're going to find both answers. So we get velocity final 1 could equal 5 plus 15 divided by 2, which is 10 meters per second. Velocity final 1 could also equal 5 minus 15 divided by 2, which is, divided by 2, which is a negative 5. Okay, so those are our two options here. Now, in order to see which option we actually want, we have to go back to our original, not original, but we have to go back and look at that equation for mass 1, because mass 1 is something that can't be negative, right? Velocity can be negative, but mass can't. So our mass 1 equation that we used in this mess of algebra was mass 1 is equal to 30 divided by 10 minus v final 1. So if I plug in 10, a positive 10 in for v final 1, do you see how I get 0 on the bottom, right? If I get 0 on the bottom, that's not good. I don't want to divide by 0. It's just not a good thing to do. So because of that, that means I'm actually going to throw out that answer, and that means my answer for v final 1 is actually that negative 5 meters per second. So since it's negative 5 meters per second, in order to find mass 1, I then am going to plug in my negative 5 there. So I get mass 1 is equal to 30 divided by 10 minus a negative 5. And so here I get 30 divided by 15, which is 2 kilograms for mass number 1. So this whole mess of a video was to show you that it is possible to do crazy problems like this where you don't have many givens and you have 2 equations, right? We have conservation of momentum, conservation of kinetic energy, and you can use those 2 equations in order to solve these problems without memorizing those fancy equations that they give you in the book. However, it is very, very time consuming, but it is possible. Okay, so I did want to show you that. If you want to see it done with the fancy equations in a much more painless way, it is on page 239 in your book. So I recommend you guys going to actually look at that and seeing how it's done with those equations that I gave you in the video lecture as well.